So to wrap up our study of tree-based data structures, we're going to look at one particularly useful application of trees, which is representing a program. Think about any Python program that you've written. There's going to be maybe some classes, definitely some functions probably, dozens, maybe hundreds of lines of code. As humans, we read and write code as text, and so we take for granted the fact that we can get the computer to run our code and do some pretty amazing stuff. But what actually happens when you run a program? Well, another program, which is called the Python interpreter, takes our file and runs it. But as you've probably seen at this point, writing a program that works directly with text can be hard. Reading a string of characters, extracting meaning from them, requires a lot of fussing around with small details. But there's a bigger problem with working directly with text. Strings are a linear structure, but programs, whether it's Python or another language, are much more complicated than that, and in fact generally have a recursive structure. For example, you can put for loops and if statements inside each other as many times as you want in whatever order. So the first step that the Python interpreter takes when given a file is to parse the text from the file and create a representation of the program, which is called an abstract syntax tree, or AST. The tree part is significant. Given the recursive nature of Python programs, it's natural that we'll use a tree-based data structure to represent them. Probably not too big a surprise. So we're going to explore the basics of modeling programs using these tree-based data structures. We're not going to be able to model the whole Python language in such a short amount of time, so we're going to look at more of a straightforward part of the language, just simple expressions to be evaluated. So in Python, an expression is a piece of code meant to be evaluated, returning the value of that expression, as compared to, say, when you write def to define a function or class to set up a class. Expressions are the basic building blocks of the language. You need them to compute pretty much anything. But because of the variety of different expression types in Python, we can't just use a single class for every kind of expression. Instead, we'll use different classes for different kinds of expressions, but use inheritance to make sure they follow the same interface. This will set our implementation of expression trees apart from tree representations we've seen in the course so far. So, starting off, here's an abstract class. EXPR, an abstract class that represents a Python expression. And it's going to have a method called evaluate that returns the value. And for now, we're going to just raise an error because it's not done yet. Now notice we haven't specified any attributes for this class. Every type of expression will use a different set of attributes to represent the expression. So we'll look at two types of expressions for this. First, the simplest type of expression is a literal constant. So we have 3, hello. And we're going to start by just representing numeric constants like integers and floating point numbers. As you might expect, this is pretty simple with just a single attribute representing the value. So if we have an expression of a number, num, it's going to have the number itself. Self.n is the number that it represents. And when we want to evaluate it, hey, guess what? We return the value itself. Not really too tricky there. So you can think of constants like this as your base cases or your leaves of your abstract syntax tree. Next, we're going to look at ways of combining these into larger expressions. So here we have BINOP, arithmetic operations, specifically binary operations. So the obvious way to combine numbers together is through arithmetic. Add the numbers, multiply the numbers, that kind of thing. So in Python, an arithmetic operation is one that consists of 3 parts. Left and right sub-expressions, which are the operands, the things that we're operating on, and the operator itself. And we're going to have a class for this. Binop, an arithmetic binary operation, and it's called binary because there's 2 things we're working with. It's going to have the left operand, left, the right operand, right, and the name of the operator. And left and right both can be expressions of their own, and the operator is going to be a string. And we're going to keep this simple and stick with plus or multiply. Now, note that the binary operator class that we just made is pretty much a tree, right? The root value is the operator name stored in the OP variable. This could be plus or multiply. And the left and right subtrees, quote unquote, are the same type of class as this. They're both expressions. So we could represent something like, say, 3 plus 5.5 in the following way. We make a binary operator. We have the left operand to be the number 3, which is an expression, the right operand to be the number 5.5, also an expression, and the operator we use on them is plus. But of course, the types of the left and right attributes here aren't num, they're expr, they're expressions. So either of these could also be a binary operator. So something a little more complicated, we got what we just did. We could multiply that by 0.5 plus, then in parentheses, 15.2 times negative 13.3. And what does this all break down to? Well, it's the operation of, and if you kind of look at this from the outside in, you can see here we're going to have multiplication be sort of the last thing that happens. So that's multiplication here. On the left side, we have this first binary operation, the addition of these two values. And on the right side, we have something a little more complicated. If we look again from the outside in, the plus is going to happen last. So that's this plus here. And on the left side, we have 0.5. And on the right side, we have this equation, which is also its own binary operation. As practice, recommend for you to put together maybe a statement kind of like this one, an expression like this one, that has, let's say, at least 4 different left opening parentheses, and you can close them in whatever order you like. Try doing it and seeing if you can represent that mathematical expression with the code that we've designed here. Now, it might seem like this representation is more complicated, and it certainly looks a lot more verbose. But we must be aware of our own human biases, right? Because we're used to reading expressions that look like this. We've been taught how to do so in our math courses and such. So we take it for granted that we can quickly parse this text in our heads to understand what it means. Something like the Python interpreter does not have a head, right? A programmer needs to have written code for every possible action that the interpreter could be taking. And this is where something like our binary operator class really shines. To evaluate a binary operation, we look at the left, we look at the right, and we combine them using the operator that we've chosen. So this code is pretty simple. To evaluate, we evaluate the left side, which is an expression. We evaluate the right side, which is an expression. If we're trying to add them, then we return the sum. If we're trying to multiply them, we return the product. And if we got an operator other than plus or multiply, we haven't correctly come up with it yet. So even though the code for this looks simple, it actually uses recursion in a very subtle way. Notice that we're making pretty normal looking recursive calls, left.evaluate, right.evaluate, that match our structure, but where's the base case here? We don't have a base case in this. So this is really the significant difference between our expression trees and the tree-based classes we've been looking at. Because we're using subclasses of expression, there's a bunch of these different evaluate methods. So we're not always calling this one that you see here. Sometimes we're calling, where is it? I'll find it. This one, which look, it just is a base case. As it is, you just return something. No extra work needs to be done. So, going back. Each time self.left.evaluate and self.right.evaluate are called, they could be this same one again, or they could be the basic number evaluating, depending on the values. And now note that the original one, the one that just returns the value directly, does not have any recursive calls at all, because it just returns n. This is the base case, and it happens to be located in a completely different method. So fundamentally, evaluate is still an example of recursion. It's just one that spans multiple classes. Now, of course, Python programs are more than just simple arithmetic. And so in this course, we're only just kind of scratching the surface of the full set of classes you would need to do if you wanted to represent Python code. But even though a complete understanding is, outside of the scope of this course, what we're doing here is not just a theoretical thing. This is part of the language itself and tools that work with the language. Turns out there is a built-in Python library called AST, short for Abstract Syntax Tree, that uses the approach we're talking about here, but is obviously a little bit more comprehensive, covering all of the Python language. If you want to learn more about this, there's a link right here that you can check out to document exactly what's going on.